welcome back to my YouTube channel. Today I'm talking about my second book, Narrow Cryptography using Keras and R. The book's freely available on my website, that'swithR.com. And in it I go through one method of using neural network to encrypt messages, or data in general. So there's 4 parts. And my intention at the moment is to make this a 4-part series where I go over part 1 in one video, part 2 in the next, and so on. And yeah, we're going to go through this method I created for embedding messages in matrices using neural network. So this video can be dedicated to part 1, which is just a refresher on neural network-based multi-class classification. And we're going to use that type of methodology to encode different characters, and that character encoding is going to be carried through the whole book. Okay? So the book's freely available online, like I said. That'swithR.com, my website. I'm actually going to use a Word document instead of this text right here, because the one thing you can't do with this text online is copy and paste. Every page here is actually an image, not a document you can copy and paste. And I'm going to use this Word document right here so I can copy and paste code and make it go a little bit faster. Because there are a few places where there's larger blocks of code, but I don't want to include it on the website because I don't want my book just copied wholly and provided other places. So, with that said, let's get started. So you need Keras and you need R, of course. I go over that in my quick start guide, but I'll go over it real quick again. So you need to have R in RStudio. You need to install Keras, and you need to use the install_Keras function to have Keras to install TensorFlow in the backend. Because Keras itself is not a system for making neural networks. It's a layer on top of TensorFlow to make neural networks. So, if you don't already know what's going on with neural networks or how to get started, I have a book, Neural Networks with Keras and R, also available on my website. And I have a series of 11 YouTube videos that cover getting started with R and the basics of neural networks with Keras and R. So that's a good idea. If you have a NVIDIA graphics card, it's a good idea to try to set that up. I don't have instructions for that because it depends heavily on the operating system, and it feels like the instructions for that changes over and over. One month will be one set of steps and the next another, so that's going to have to be something you pursue independently. But you don't, for this book, you don't have to have a graphics card. It really doesn't matter with the network we're making. It's a little bit about me. I have a master's degree in psychology and a master's degree in applied statistics. I took PhD level coursework in deep learning. I fell in love with the subject, and I wrote 2 books about it. Okay, so also, it's important to note that I am not an expert in cryptography, and I am not saying that these methods I go through in the 4-part series are robust to modern hacking techniques. I don't know. The only real way to know is to submit it to a large community of essentially hackers and have them try to hack through it. I've not done that. I have not done no such testing. So it is really just a fun project with neural network. That's what I'm trying to get at here. I'm not asserting that this is going to be a foolproof method of cryptography, because it certainly is not. Okay? So, a note about the function. I have a series of functions I define throughout the book, and you can find them in the appendix. I'm going to go here and so at the very bottom of the book. Okay. So I have a list of functions, the name, and a description of what they do. And I believe there's 12 of them. So if you see a function you don't recognize, or you just don't remember what it does, it will be described in the appendix, along with the full code for it. Sometimes in the book, the code gets a little off, and it might be slightly hard to read, but in the appendix, I did my best to describe the functions and write them out as clearly as possible. Okay, so getting back to the Word document. So for the first part, I'm just going back over using a neural network to conduct multi-class classification, and yeah, so we're gonna. So I talk about it at some length in the book. It's of course good to read, but I'm gonna go ahead and get started with the code. So of course we need a library Keras. It's installed in our computer, but every time we restart R, we have to library it. Okay, so I'm making a set of dummy predictors. It's not a matrix of random values from the uniform distribution. 1000 in column equals 10. That means the number of rows would be 1000 divided by 10, or 100. So we have to make our outcome, which is going to be a matrix of 100 values. I picked the standard normal. And the point of this is not to show a real world example, of course. It is not a real world example. It's just the basic nuts and bolts of doing the one. So we have 10 predictor columns and 1 outcome column. And the first thing we do when we're creating a neural network is we, instead of a neural network data type, essentially, that we build off of, and we do that using Keras model sequential. There's other options that are more advanced, where you can define recursive neural network and things such as that, but that's not what we're doing. So, okay. So now we call the neural network we just created, use the pipe operator found in the tidy first, and then we start building a neural network. So it's a layered in the unit, the activation, which is going to always be Rulu, except for the last layer that changes depending on the type of neural network. And in the input state for the first layer, and then for the subsequent layers we just do units and activation. We don't do an activation for a continuous outcome, and that's why that's not there. I'm just going to copy this code, because I feel like it would eat up some time to do it manually. Okay, so there's our neural network. And then we have the compile step. Oh, I just typed in my book. Whatever, I'm not going to worry about it. Now we have the compile step. Then we call the neural network again. Compile log equal MST, mean squared error, which is appropriate for a continuous variable. Optimizer, it's always going to be Atom as we go through. So optimizer Atom. And it's not being quotation, it's a function. Okay. Optimizer Atom. Perfect. And we don't need a different metric. You could pick something like MAE, but there's no need to do that per se. Okay. And now we can have one more step, the fit step. So history, this variable stores the training history, that's why we call it history. And so we have demonstration neural networks, and then what we want to do to it. And we want to fit. Predictors, comment outcome, epoch equal 10, bat size equal to 16, and I don't care to set for vote equal to 0 because I don't care how long the output is in the console right here. So control enter. And it's going to give me a whole bunch of errors because it's not set to train on a CPU. And there we are. Didn't take very long at all. We had essentially no data. And in the book we ended up with like 0.8. We started higher here. It doesn't really matter. So you get some plot. It trained a neural network and the loss function decreased. Okay. So this is a neural network architecture was intentional. We started with an input size of 10. Went to 100, 200, and then back down to 100, and then to the final output size of 1. So it started small, ballooned out, and then went back to small. If you define a different neural network style, like let's say we turn that 200 into 10, it's not going to be very happy. Because what you're doing is artificially restricting the dimensionality of the data right in the middle of the neural network. Okay. So for the same random data generated, we went down to a loss of 1.11, whereas before we went down to 0.9337. So there is some thought that needs to go into your neural network architecture. I think I'm generally going to start with a low dimensionality, balloon out, and then go back to the low dimensionality. It's kind of like a diamond type architecture. And you see that same type of output in the book. Okay, so in my previous book, I talked about a function called toCategorical that one-hot encodes categorical variable. I dislike that function, and even in the book, I go through some trouble to make the function happy with the type of data I'm inputting. So one of the first functions we're going to create is a function that replaces two categorical with a custom function that does the same thing. It one hot encode categorical variable. Okay. But first we're going to do a new neural network that is actually a multi-class classification. Okay? I'm going to leave that alone. So I'm going to try to repurpose a lot of this. So I want an intermediate, two intermediate lines. So option. Oh, and that's a R function in base R. So option, option. Okay, so we're gonna go with that. That didn't used to be a problem. I think that might have been added. Rabbit and fifth. So these are the 4 different categories our variable can take. And then we have the option indexed. So we have to pick we have to sample from this list 100 times to get a list of 100 outcome variable. So that's what we're doing. The sample 1 through 4. So that's the vector we're sampling from. So we can get a 1, a 2, a 3, or a 4. If we want to do that 100 times, we get out the number of the length of the vector we want. And replace needs to equal true. If it doesn't equal true, it's going to sample 1 and then never be able to sample that again. Sample 2, never be able to sample that again. So basically, you can only have a list of 4 items without replacement. So you need to replace, or this function will throw an error. So we're just about to the point where we can do this. Option index. And then outcome 1 hot encode. So outcome 1 hot encode is the thing we are going to feed into the neural network. So run that again. Option. I'll go into environment. So that's a vector of length 4. Option indexing. This is a vector of length 100 that contains randomly sampled values from the numbers 1 through 4. Outcome. That now actually has the not 1 hot encoded outcome right here. And then we have the 1 hot encoded outcome right here. And I don't know why, but it also contains a 5th column. I don't see any values in the 5th column. Let's go ahead and test that. So, sum outcome 1 hot, and that's a matrix, right? Yeah, that's not a data frame, so I can't do that. I have to do this. So I want all the rows of column 1. Yeah, it created an empty column. I have no idea why. And I don't really care why. We're going to replace that in a minute anyway, so I'm just going to leave that alone. Okay, so that's good. there's nothing wrong with that first layer. I want to put this back to 200. Because the point I was making is the problem. Okay, so we're going to make our activation softmax, which forces the output column to all sum to 1, the prediction. So the output are due to probability, because the probability of being in any column had better be 1. The probability of an outcome needs to be 1. Okay. So we need a different loss function because MSE is inappropriate for this task. We need categorical cross entropy. I just need to spell it right. Entropy. And it's not strictly necessary, but I'm going to add in accuracy. Vector equal to accuracy. It is not going to be very accurate because the predictors have absolutely nothing to do with the outcome. It to be about 25% accurate. Although we got that extra column out of nowhere, so it might actually be more like 20% accurate. And that's fine. Okay, so I believe we're good to go, and let's run it. And I've made a mistake. Oh, I know that's what I did. Predictors. Don't want outcome, I want outcome when hot. Okay, so it's actually mad here. Maybe I could actually copy the code. Okay, here we are. Okay, so the accuracy went up to 45%, and the loss went down. That's actually deceptive. It did not do nearly as well as it could have. I'm going to go ahead and do a validation set. So what's that called again? I want validation. Okay. Give me 1 second. We're going to look this up. Okay, so we're going to go to my other book. I'm going to go all the way down to where I talk about neural networks. And I just need the little bit of code that talked about holding out a validation set. Because that accuracy is deceptive, the things really are not related at all, but it's sensitive. Compile. Okay, perfect. I put it in the wrong place. Sorry about that delay, everybody. Validation split 0.2. I'm going to go back to the Word document. And when we run this, we're going to find that it's not nearly as good as it said it was. The validation accuracy is about 0.3. Where the training accuracy on the data 0.48. If I train this a lot longer, we'll get 100% accuracy on the training data and terrible accuracy on the validation data. Because there is no relationship between the predictors and the outcome, like I said. It's all just noise. Okay, perfect. This is a better representation of what I'm talking about. The training accuracy goes to 1, because the training accuracy will always go to 1. The loss on the training data goes to 0.14, but the validation accuracy is uniformly terrible, and the loss goes very high. This is a red flag. This tells you that you're overfitting. And what we really have here is no real relationship between the predictors and the outcome. Okay. I should have put in a validation step here, just to demonstrate that even though we're getting this high accuracy, it's really an illusion. There's no relationship between these variables. It's only modeling noise. Okay. So now we have the text to matrix function, which is going to replace the 2 categorical option. I'm going to open a new file just so I don't end up deleting my neural network code. And we're going to talk about what this does. I'll talk about it in one block of code at a time. So I'm going to actually type out text to mat. And this is going to be our one hot encoder function. So we have the input of the vectors categories, like the other function, identify. And what this is an option to tell the function to identify the levels of the category. And this is an optional vector of the possibilities in the category. You can imagine situations where you have possibilities in your data that aren't reflected in this actual data. Let's say you have animals, and you have 50 different animals it could be, but your data only contains 20. If you want to in this function, you can turn identify off, and then insert possibilities of animals, so all 50 possibilities, and then your one hot encoding will consider all possibilities of animal, not just the 20 possibilities you gave it. Okay? I'm going to copy that right over to here. Okay, so we have the first line. Let's just make sure the input is character instead of other data type for consistency's sake. If this value has been changed, then we take that. Yeah, it's not null equal true. Yeah, so if this value has not been changed, my apologies. We use the input data to generate the possibility. If a value has been input for goodness, the possibility, then we just use the value given as the possibility. I run this line of code for the outcome previously. So name, table, and then outcome instead of input. And we just get the names of the input. So that's assuming that all the possibilities are the data we gave it. We cannot have a tiger because tiger was not given. But we can have a tiger if we manually input that a tiger can exist. Okay? If identifying is equal to true, at the end of the code running, it will tell us the possibility. So we don't have to guess at the possibilities it found. It will tell us. So that's not necessarily for the code to run. It's just a helper function to make it a little bit easier on us. I'll go ahead and you'll see it run. I don't need to run it. Okay, so these are the actual loops that do the heavy lifting. Paste. Okay, so this is a for loop that goes through each input value. And then it also goes through each value of the possibility. The possibilities are either the possibilities it's found using this line of code, or the possibility we provided to it using the POSS argument. So it basically defines the indexes of everything. Let me go ahead and do that. So I'm going to set path equal to outcome. And run this line. Oh, and I need to set input equal to outcome. I made a mistake. I should not have done that. Path needs to be equal to, my apologies, name table outcome. Okay, so what this code needs is that the possibilities are a cat, dog, fish, rabbit, and the outcome is a list of those. Effectively, I should say, get a list of the okay. So let's go ahead and run that. Okay, so the input used to be the outcome, and now input is a vector of the indexes. And you'll also see that these correlate with the option indexes. They're slightly different. It is a different order. But yeah, there's a different order between option and path. But yeah, so we're taking it and turning it into indexes. And then we need another loop to take those indexes and break them out into different columns that we call one-hot encoding. So we're going to take it and break it out into different columns. Copy. So we make an empty matrix and fill that matrix for each column. And when we do that, so the first input's 3, and we have a 1 in that third column. Second input, 3 again, a 1 in that first column. We go to 1, 2, 4, and so on. And then the last step is to return this matrix. The return function, so to insert that what we want outputted from the function is what actually gets outputted from the function. There's nothing fancy to it. So this is a superior one-hot encoding in my opinion. We don't have to worry about data types as much. It's much better at forcing things, and it's much better at accounting for variables, options that are not in the training data. So we don't have to have a tiger to know how to handle a tiger. We just need to tell the function here in the possibility that a tiger is possible. Okay, so I'm going to finish this up by writing a return, and then I'll run this whole function to save it to the environment, and then move on. Okay, I'm going to go back, and then take true categorical out, put text, to mat in, and we'll see that it all works exactly the same. Perhaps even better. Yeah. The accuracy is always going to be bad because the predictor is not related to the outcome. And that's fine. We're going to deal with situations where they are in a second. So we have outcome one hot, and it works just the same. Okay. Except we don't have an extra column, and we don't have to worry as much about data type. And we can supply the function with all the possibilities, not just the possibilities, in that particular training data. Okay? So now we're going to do this on some closer to real world data. So I'm going to go in here and call data iris. And that's on the same line. I'm going to call that flower instead of iris. I feel like it's more descriptive. And I don't like how data loads naturally. And it just forces it to be better. So flowers dataset, it's not the iris dataset. We have 4 predictors, and then the outcome, which can be either Satosa, first color, and I'm probably butchering the pronunciation, or Facinica. But yeah, so it's multi-class classification with 3 different levels. Oh, and I should point out that identified with equal to 3. So it told us the different categories. It was actually 1, 2, 3. Oh. Because I had option index here, not the outcome. Goodness. I don't know why I would have done that. Okay, so outcome. And clearly you can use this to as a sanity check. Okay. The categories identified are cat, dog, fish, rabbit. Just like we would expect. That's not really going to change the neural network training. I just missed the naming. I probably did that in the other training too. It's doing this stuff while recording hard. Okay, so I already showed you what it looked like. Head is the first in rows. Okay, so we're going to do a row example where we break out training and test data. That's a great idea. I'm going to go ahead and get rid of that code and do this real example. Okay, so we want to set the seed. It doesn't really matter where. I do it right here. Set dot seed. 1, 2, 3, 4. And what that does is make sure we split it. I split it the same way you split it. There's no index. Selection. I think I'm going to start copying code. And okay. So what we're doing here is we're taking 70% of the data, putting it in 1, and then sample 1 round. I see. Okay. Yeah, so we're sampling basically 70% of the data. I see. And this is going to be put into training, and then we'll use 30% for test. I'm going to go ahead and copy all that code. It's a basic training template. You've probably seen it before, and I'm not going to take too long going through that. My code's getting kind of long. Hopefully not below my head. Okay, so this should be good, I believe. Let's run it. Don't need a library again. Okay, I need to be right here, actually. So, I ran all our code. And as a sandy set, because apparently I need it. It identified the category correctly. And as you might have noticed, the categories were ordered. So there were 50 Satoshi, 50 Verticolor, and 50 Vicinity. Let's go ahead and look at that. So, training, flower outcome. And actually we randomized it. So it won't be in that same ordered nature, but it looks good. 3 columns, and I'm sure that's correct. I'm not going to worry too much about that. I don't need to worry too much about the neural network. I just need to change the input in my fit. So training. What's going on here? That's the problem with copying code. The training flower. Training flower. Okay, what do I do with my neural network? Taking me a second to... Oh. It's not a very good idea to standardize. I did not do that. Standardization is a good idea. Okay, so yes, we want the prediction and outcome. Okay. Sorry about that. The training, flower prediction. I think I'm safe as long as I don't go below the recycling bin. Training, flower, outcome. Okay, so hopefully this is going to run. I don't have to debug. No, it's very mad. training flowers outcome. Training flowers outcome. And this needs to be training flowers spread. It's a good idea to standardize. It's not strictly necessary, but it's always a good idea, especially if you have extreme value. The extreme value can make the gradient descent algorithm work harder. Okay, I stand corrected. It will break it if you don't standardize your training data. Brilliant. Okay, so that was my mistake. I neglected to standardize, and the gradient descent algorithm would not work. Okay. So we can also incorporate dropout layers. I'm going to go ahead and put the validation split back in to demonstrate that. I can't believe I made this mistake. And it actually, the validation and test data look really good. They're right on top of each other. But if you have a problem with overfitting, you can use dropout, just like I did in my previous book. And that will help with overfitting. Okay? And I believe that we're getting towards the end here. You can also use the neural network to predict classes. Okay, and we're getting into part 2, where we take the multi-class classification framework and we use it on a set of 85 character variables to encode a method. Okay, that's the end of the video. Thank you for watching.